Okay, thanks so much for the invitation. Really excited to be here, talk about Anycost and any resolution image synthesis. So the last few years have really been watershed years for image generation. We have many groundbreaking generative models, and they'll soon serve as the backbone of many creative applications. Yet in some respects, these models are still limited. So when you and I develop models in the lab, we typically are working with a few constraints. For one, we're all using GPUs or TPUs. Typically, we're asking our advisor or our managers for as many GPUs as they're willing to give us, and we're filling them to the brim and just getting the best model that we can have. In addition, when we're training our generative models, we assume that our images come in these fixed size data sets. But if we zoom out just for a second, we see that our algorithms are really looking at an artificially homogeneous slice of the world. In the world, there's really a much larger diversity. There's a diversity in the types of devices that users are actually using, and images comes in all different shapes and sizes. And by not accounting for this, our algorithms are missing out. So in this talk, we'll look at two works addressing these fundamental issues. The first, Anycost, looks at creating flexible models, which can be used in different computing platforms. And the second, Any-resolution, looks at taking advantage of models or images at their native sizes. While we examine these issues specifically in the context of GANs, these are actually underlying issues across different generative models, and we should be considering them. Okay, let's start with Anycost, and we'll start by just showing an example GAN-based demo here. On the left, we have an input image we'd like to edit. We have these nice sliders that are in a GAN latent space, and on the right side, we'll show an output. So a user may come in, take Ryan Gosling. We'd like to make him smile. And we see that the user clicks, but they have to wait quite a bit. And if they want to try again, they need to wait again. And this becomes kind of a difficult kind of interaction. Now, why is that? Let's look at what's going on under the hood. We have an input image. We need to project that into the latent space to find our specific input image. That's kind of expensive, but we only have to do that once. Once we have that latent code, the user can we can expose a bunch of sliders to the user, which effectively moves this latent code by a little bit in a strategic direction. And then from there, we need to put that latent code through a generator. Now that's typically being run on device on a person's computer, and that can be slow, especially when you consider that usually repeated adjustments are needed. So the user is going to be just spending a lot of time waiting for this generator to run over and over and over again. So here, we'd like to ask, can we improve the user experience? And our proposal is to have a fast, low-cost generator that can provide an accurate and reasonable preview to the user in order to make their experience better during interaction time. Okay, let's consider what properties we'd like to have in this smaller and faster generator. Okay, so first, downstream at test time, this generator may be used in all sorts of different devices. So one thing we'd like to do is enable flexibility across different computing constraints. Number two, let's say this image came out, we probably wouldn't be very happy because it doesn't look realistic. But we don't just care about realism. If this image came out, we'd also wouldn't be happy because while it looks okay, it's nowhere near an accurate reflection of the full generator's image. So we also care about consistency. So we'll be considering these three aspects in designing this smaller and faster model. For the first, to enable flexibility, our proposal is to train a single generator that's reconfigurable at test time, depending on how much compute budget you'd like to use. And from here, we'd like to really discuss how we go about training the training procedure and the architecture for such a generator. And we discussed this in this work that we published in CVPR of last year. The first author, G, was an intern with us and was really great. So to start off, we can examine the StyleGAN 2 baseline. Roughly, it starts with a core set of layers and progressively refines them into something until we get a final image. And that final image is put through a discriminator, which supervises the generator and makes it hopefully realistic. Now, one way of saving compute is we can look at the intermediate layers here, okay? And if we are able to early exit, we can get an image out potentially with less compute. A problem with just by doing this on the baseline is these are not going to look realistic. After all, why should they? They're not being put through a discriminator. They have no real constraints, realism constraints. So our first step is to add that constraint. So we're going to randomly sample from intermediate layers of the generator and put them through intermediate layers of the discriminator. And that already starts giving us some flexibility and realism through the intermediate layers of the net. From here, we can go a bit further. We can On top of that, add some random sampling in each of the channels as well. And that can additionally save compute. So let's see what happens if we do that. Here we have an example generation using the full generator at full capacity. And that gives this result. We can then run the generator at half capacity and we get this result. While it looks okay, there's a bit of a problem. These two images don't look that alike. We actually see some large inconsistencies between them, so we're not happy. What we found is that if we add a similarity loss using your favorite perceptual similarity metric between the left and the right, this really ends up making things more consistent. Okay. It's okay? Cool. Okay, so okay, yeah, so this is the result of adding the similarity loss. And we see that while it's not perfect, the left and the right are a whole lot closer now than they were before. Okay, let's see how our model does across other configurations. So on the left here, we show a style GAN model. It requires 144, I think this is a gigamax. So this is the amount of multiplies and additions. So it's a lot of computation. Now we can look at our Anycost. Our Anycost can provide cheaper results by decreasing the resolution or by decreasing the number of channels. So all these configurations end up giving you faster results with less computation. And in fact, you can actually try combinations of these, and here's a grid of 16 different configurations, all run with one single model. And we can actually go through and look at how many operations are in each model, and we see that we get something from moderate savings, for example, saving maybe 20% of the compute, to something very extreme. If you look at the bottom right, that only uses 5% of the compute. So this kind of gives you some space to traverse in between quality and compute. And the good thing here is that all these generations look reasonably close to each other. And in fact, I can show you this by traversing latent space, and we see consistencies all through the space, which is our desired property. Okay, how are we actually going to use this in practice? Well, here's a demo. Now recall, before it took about 4 or 5 seconds to get a result. Okay, so now we can reduce the channels, reduce resolution in the generator, and see what happens. Okay, so now things are a lot snappier. Our interaction is less than a second, so it's almost interactive, and the user can really ideate much better. And in fact, we can be even more aggressive and reduce the channels even more. And now we have something at 1/3 of the second running on CPU on my MacBook. And this really allows the user to have time to play with a whole bunch of different sliders. You can change the young, old slider, remove some of the eyeglasses, and change the hair color. And once the user is kind of happy with their result, in the end, they can still run the full network when they're done ideating and get the full quality result. So they can run the fast generator during ideation and the full generator during idle time, and really get the best of both worlds in this case. Okay, so one thing we'd like to note is that there are preview modes in all sorts of different software, for example, rendering or video editing. And part of this work is to try to enable this as kind of a goal. Maybe all generative models should come with a fast preview mode kind of built into it. The code and models are online if you'd like to play with it, as well as that demo that we just had a recording of. Okay, so in this previous work, we were strategically decreasing the resolution for cheaper computation. Of course, we're also interested in improving the high-end quality of our results. And one way of doing that is increasing resolution. Now, this is actually quite difficult to do beyond 1024. One aspect of this is the higher resolution you go, the less data you have available. And really, we took a step back and thought about why is that? Well, the reason that is actually our data construction processes are actually very wasteful. So if you go on the internet and just scrape a bunch of internet images, in the wild, you're going to see different images of different sizes and shapes. From here, we actually all do something very sad, which is we put it through a filter. So the small images, too small, we throw them out. Big images, we end up downsampling away. So here we're throwing away lower resolution images as well as higher frequency information. And so these are pixels that a downstream model never even gets an opportunity to touch or learn from. So we'd like to relax this constraint a bit and do something simpler. We'd like to come up with some sort of training scheme so that we can simply use any image that we want. And this here we're going to call an any resolution data set. Okay, one such way of building such a data set is to leverage the work from other previous researchers. So one way is you can take an existing LSUN data set. This contains over 100,000, well over 100,000 images, for example, of churches. And on top of that, we can go on Flickr and just find a relatively small number of high-res churches. This case is about 6,000. So this is about, it's kind of like sprinkling on 5% more data in terms of image count. And all these images potentially offer value. We'd like to learn the structure, leverage the structure of the low-res images, as well as the details from the high-res images. Okay, so how are we going to come up with some sort of training scheme that's able to do this? Okay, so we explored this in this recent work that we put on arXiv called Any Resolution Training. And the goal in the end of the day is to produce a very high quality, high resolution synthesized GAN or image. Okay, and the first author here is Lucy Chai, who is a really great intern working with us this past summer. For this, we started with the StyleGAN3 architecture. Part of that is because it offers something very useful. Not only does it, do you input the latent code, but you also actually input the coordinates of an image. So you can think of the top left of an image as 0, 0, the bottom right as 1, 1. Each of the pixels are a specific XY location on that image plane. And you can input a grid of pixels into the generator. And that's what StyleGAN3 does. Now, some simple modification that we can make that we realized was that you can actually increase the sampling rate in that image grid and put a denser coordinate grid into the generator. And you can then see if the generator outputs a higher resolution image for you. We also found it advantageous to directly inject the sampling or scale, or the sampling rate or the scale into the generator. Okay, so now we have the single generator that can potentially produce images of all different resolutions. This does lead to one problem. Because all of our pipelines and frameworks are for fixed resolution data sets, we're not going to be able to do batching, right? Usually you have fixed the same resolution image, you stack them in a batch, you get a nice 4D tensor, and you can start doing processing. But we can't do that if all the images come into different resolutions. So we need to find some way of batching multiple images of different sizes together. Okay, to do that, there's another additional trick that we can do, which is instead of inputting the XY coordinates of every single pixel in the image, we can just input the coordinates of a single patch. And because of the fully convolutional nature of the generator, you can then directly get just a single patch out. Okay? And that means that if you look on the left, we can actually query a different resolution image, but we can get the same size patch. Actually, this insight was also made in some concurrent work in this conference, so I recommend you check that out. Okay, if you look on the left here, we can also sample a slightly lower resolution image, but grab the same size patch, or we can even do that quite aggressively, an even lower resolution, but the same size patch, where we see more context. Okay, so through this operation, we can take advantage of the architecture of the network and batch same size patches that come from images of different scales. Okay, so from here, we're almost golden. We can query our generator for a bunch of high resolution patches. We can take our any resolution data set, perform cropping to do the same operation. And now we have a nice set of real patches, and we can put them through a discriminator as we do. Okay, so this scheme here is a patch-based training scheme that allows us to directly try to get high quality, high resolution patches. Now you may be thinking there could be a problem here. How do you maintain global consistency? How do you know that the head of the bird isn't going to appear where its feet are, and vice versa? So for here, we found that a little bit of structured guidance from a low resolution generator helped. So we can write our previous objective out like this. We can have another generator that's trained on low resolution images. Okay, and that can, once again, you can leverage previous people's work. You can go on a model zoo and download a pre-trained model, for example, one that's at 256 by 256 on LSUN, or you can train your own. Okay, the question here is how do we compare a low resolution image to a high resolution patch? They're kind of different objects, but because we know the geometry, we can just take a crop from the image, we can downsample the high-res patch and put it through a similarity metric again. And there we get our final objective. Okay, so we have these two loss terms. One is aimed at high resolution quality. The other is aimed at getting structured guidance from low resolution, so kind of like scale consistency. And this lambda term actually ends up trading off between the two. Now, in the previous project, we really didn't care a lot about consistency. In this project, we really cared much more about pushing the envelope on high resolution quality. That's really the primary priority here. And we'll show some examples of why that is. So we can show a comparison versus super resolution. So one way of getting potentially a high resolution GAN is you can take a low resolution GAN trained on LSUN at 256, for example, and put them through super resolution algorithms off the shelf. Okay, so we show a comparison to those compared to our method, which again has just about 5% of high-res data sprinkled in. Here we're going to be varying our scale parameter in order to zoom in to our network. Okay, so let's go ahead and do that. So we're going from 256 up to, I believe, 1600. So this is about a 5x zoom in, which is pretty extreme. Okay, so we see some interesting artifacts here. On the left, you see a lot of speckle patterns on the roof of this church. Why is that? Why is the GAN producing that? Well, if you look in the training set, they're actually processed by JPEGs, and these are very common JPEG artifacts. So if you look in the LSUN training set, you see speckle patterns on every single roof. And that's just a property of the data set that the GAN is now mimicking. As an aside, if you're producing your own data sets, please don't save it as JPEG, or at least have the decency to use a quality 95 instead of the default 75. Okay. But what happens here is that the super resolution algorithms are actually looking at this, and they have to decide, do we stick with this artifact or do we not? And so if you stick with the artifact, you end up just enhancing it, which maybe you don't want. Some super resolution algorithms do suppress it, but here it's not really getting the rooftops very well. And instead, we're getting a much more realistic high resolution rooftop here. Okay, so I like to explicitly say that we are not doing super resolution, even though the task looks similar. Unlike super resolution, we explicitly want to have a little bit of freedom in order to fix artifacts that we observe at low resolution. Okay, let me show you another type of artifact. So this is a generation, again, from an LSUN generator. Looks pretty good, but what is going on here? Why is there a ghost of a Shutterstock logo? Well, again, if you look in the training set, a ton of the images were scraped off stock imagery, and they have this, and the GAN's, of course, going to mimic it. Now, again, if we take our model and start increasing the resolution, the Shutterstock logo starts going away, and we start getting realistic brick patterns that look kind of nice. Okay, so qualitatively, we're seeing interesting high resolution results. How do we actually evaluate that? This actually takes a little bit of thought as well. So generative model evaluation is typically done with the FID metric. The way it works is you have real images, generated images, you put them through in a feature extractor, fit first and second moments, and then compare them in a probability distribution space. Okay, now that's all well and good, but there's actually one key detail here that's often overlooked, and that's actually that these images are all downsampled to 299 because the inception network was trained on ImageNet at 299. Now there's a few issues that arise here. One is that it turns out these downsampling functions and common libraries often don't follow signal processing principles, so they actually introduce artifacts themselves. And we actually explore this in a paper in these proceedings. So please come out, check out our poster if you'd like to hear more about it. But moving beyond that, for our specific application, this is actually not what we want. Like maybe we're okay with downsampling at 299 if we want to evaluate high resolution structure. That's a reasonable thing to do. But if we're at really high resolution, like 3K, by construction now, this metric is actually ignoring all the high resolution detail that we're actually trying to capture and evaluate. So this FID as constructed is explicitly not adequate for this task, for evaluating this task. It's also taking all our different sized images and forcing them the same resolution. Okay, so what are we going to do? Well, we found just a straightforward, simple modification, made it a much more appropriate metric, which is instead of downsampling, we take 299 by 299 crops. And this we call patch FID in our paper. Okay, so let's evaluate patch FID. Lower is better. We do this across a few data sets here, shown on the bottom. Here are some results with super resolution methods, and our method is able to get stronger results by the metric. Okay, from here, we train our exact same algorithm on a whole bunch of different data sets, and we'll explore some qualitative results here. So here's an input or an image of a bird generated at low scale. We can then vary the scale and increase from 256 up to 1100. And then we can actually do a latent walk as well here at low resolution, but we can do it at high res as well. Okay, can we go even higher? Well, we take a mountain data set where the base resolution is at 1024. And here we're varying the scale. So we're zooming in here all the way up to 2800. And we can see some interesting details in terms of vegetation and dirt. Okay, here's another example. This one I like. It has some kind of interesting textures, I think, in the vegetation as well as in the water. Okay, here are some latent morphs, latent walks here in the mountains. Okay, and finally, we also trained a face model. So right now, 1024 model is kind of the highest resolution that we're looking at for FFHQ. We can specifically look at patterns in the hair and the eyes, and we can actually train our model, which is tuned on some higher res data, and we can go all the way up to 4096 here. So you see some sharpening in the hair and the eyes. Okay, and I'll do some latent walks here. So just the scale, this is our current 1024 models. Here's what 3072 looks like, 3 times as large. And we'll go ahead and do some latent walks. Okay. So here in this project, we're proposing a method to support data in its native size. And this actually allows us to efficiently increase the generation resolution well above 1024. You saw some generations at 3072, 4096. Okay, code and models are released as of about 9 p.m. last night. So you can go on our website and play with it. Okay, so in this talk, we discussed how we should design our algorithms in order to have some real world considerations. The real world has different diversities, the diversity of devices, diversity of resolutions, which we addressed in Anycost and Any-Res resolution GANs. Now, we examine these issues specifically with GANs. But moving forward, these underlying issues are actually prevalent in all our different models. For example, if you're training autoencoders, flow-based models, diffusion models, autoregressive models. My hope is that in the future, we'll be thinking about how to enable full flexibility across all types of different generative models. Okay, here are the links again to these projects. These are, like to acknowledge my collaborators, especially G and Lucy, who are the first authors of these papers and really great interns to work with in these remote internships. Okay, thank you very much.
We have time for one quick question. Come to the front if you have a question.
I have a question. I remember reading about like the Anycost GAN paper. I have a question. Like basically, I remember reading about like the Anycost GAN paper, and there's something that you guys mentioned. Like basically, if you adopt like the same multi-resolution strategy proposed by MSG GAN, that's actually going to lead to like worse results. But if you replace that with like your sampling strategy, that's actually going to increase the result. Do you have like any explanation for that?
Sure. Yeah, that's a great question. So yeah, there was a previous paper called MSG GAN where it took all the early exits and put them all through a discriminator. Somehow we found by sampling, it did a bit better empirically. I don't have great intuition as to why that is, but it's something we found. Another thing we found was that the discriminator is actually overwhelmed when you do all sorts of different random sampling through both resolution and through channels. So an additional detail in the paper is that the discriminator is actually explicitly conditioned on the generator architecture as well. And we found that that improved performance.
Okay, let's thank Richard again.
Okay, thank you.